So, in the previous session we have discussed about the chemical potential. See what we have defined. We have defined chemical potential in terms of Gibbs energy. So, what does it mean? So, it is actually the change of Gibbs energy per unit molar addition of ith component species at constant temperature, pressure and other components number of moles, right. So, it alternatively represents how a solution behaves towards any addition or abstraction of material. So, it indicates about the response of a solution to material addition in pure form, right. We are adding some specific component species in pure form. Now, this we can think a paradigm where it is not the Gibbs energy, it may be anything, any property, and that becomes the partial molar property, generalization. If we generalize it, results in partial molar property. M I bar del of Nm del Ni T P Nj I not equal to J. So, here this is the over bar M partial molar property, that is the solution property only N per unit mole, and in relation to that we must note that if I write Mi, it is pure species property. Now, what is exactly the partial molar property? What is it? In order to understand, let us discuss about a thought experiment. See, I have a solution of water and ethanol, right. The total number of moles is N and the specific volume is V. So, total volume Vt equal to Nv. Now, in that we are adding delta Nw moles of water. Add delta Nw moles of water at same temperature and pressure. Now, what will happen? The volume of the solution will change. However, this delta of Nv, which is basically delta of Vt, is, we will find it not equal to Vw into delta Nw. Vw is what? Pure species or molar volume of pure water, right. It will not be exactly the same. So, what we can conclude from here, that water as a component is unable to retain its pure species property when it is in a mixed state, right. Why it happens? Because you think that pure water, it's surrounded by other water molecules, and we know that there are hydrogen bonding. So, there is a specific interaction energy which the water molecule experience, a single water molecule experience once it is in a pool of water, right. However, if the same water molecule we think in a solution of water and alcohol, now its immediate shell will be surrounded by water as well as alcohol molecules. So, the nature of the hydrogen bonding and the subsequent interaction energy will also change, and as a consequence its property will change. So, the individual component species, they are unable to retain their private property or pure species property once they are in a solution, right. But how to quantify that? Here we may think that there is some effective volume per unit mole, VW tilde, and it is defined as what? Delta of NV by delta of NW, right, at constant temperature, pressure and Na. But this VW tilde, it is a function of how much water molecule we are adding into that system, right. If we plot VW tilde with respect to delta NW, we will find that it depends on delta NW, how much we have added, okay, how much we are adding. So, the thing is, we can reduce or we can eliminate the dependency if we put a limiting condition, that is delta NW tending to 0, right. So, to eliminate the dependence, we consider a limiting situation. That is delta NW tending to 0, and we get partial molar property at limit delta NW tending to 0, delta of NV by delta of NW at constant Tp Na, and that gives rise to d of NV, d of NW at constant Tp Na. So, that is nothing but the partial molar property, right. So, this is the partial molar volume of water. So, we have got a basic understanding regarding what is referred as partial molar property. It is a property per unit mole what a species, component species must have once it is in a solution, and that is why it is divergent from this pure species property. So, once we have got the basic theoretical framework regarding this partial molar property, next we will try to generate some relation between the pure this specific solution property M and Mi bar, whether there is any functional relation between them and what are the inherent properties of this Mi bar, that we will try to understand. So you see that the total solution property Nm, that is basically MT, total solution property. It's a function of what? Temperature, pressure and N1, N2, Nn. It's obvious because the total solution property must be dependent on temperature, pressure, two canonical variables and all the numbers of moles. So, if I apply chain rule, d of Nm equal to del Nm del T at P Ni dt plus del Nm del P at T Ni dP plus I equal to 1 to n del Nm del Ni at Tp Nj I not equal to J dNi. Right, this is necessarily the partial molar volume or partial molar property Mi bar. So you can further see, split the differential. Try to understand the physically what does it mean? N, if I write n dm plus m dn, we can always do that. We can always do that. Mathematically, it's very simple, right? It's a simple rule of this product differential. But physically, what does it mean? The total solution property we may change, right? We may change in two different ways. What are the two ways? If two fundamental ways. If I am keeping the number of moles same, however, if I change the temperature and pressure or maybe the composition, right? The composition we are changing, we are keeping the total number of moles same. So definitely the specific solution property M is going to change, but the total number of moles remains same. So in this way we can change the total solution property. Alternatively, if I am keeping the temperature, pressure, composition, everything same, but we are increasing or reducing the amount, that is the total number of moles we are changing. So again that total solution property is going to change. So that's this contribution. Okay. Now on the right hand side you see in this derivative Ni is constant, that means summation of Ni, which is n, that's also constant. So n we can take out. So it will be del m del T. However, m depends on composition because this n is a extensive variable. The respective intrinsic variable will be what? Xi, the mole fraction. Okay. So write P and Xi because m depends strongly on Xi. It depends on n as well as on Xi, right? So dt, and here Ni is constant, so we have taken out this n as it is constant because n is summation of Ni plus n del m del P at T Ni dP plus Mi bar dNi, and Ni we can write as Xi into n. So further we can write this as n into del m del T at constant Pxi dt plus n into del m del P at constant Txi dP plus summation I equal to 1 to n Mi bar into Xi into dn plus x n into Mi bar into dxi. Right. Now what you can do, you see there are two terms of n, one is n, another is dn, we will group them separately. So n within bracket dm minus del m del T at Pxi dt minus del m del P at Txi dP, right, minus summation of Mi bar dxi plus dn, which is m minus summation of mi bar xi, I equal to 1 to n, capital M, that is equal to 0. Now, you see apparently n and dn, they depends on each other from mathematical sense, but physically they are not. Why? Because the amount of increment or abstraction from a solution, the number of moles in terms of the number of moles, that is dn, it is independent of what is the total amount of the solution, right? Because in a 100 molar solution or in a solution of 100 moles, we can add 5 moles, we can add 1 mole, we can add 10 mole, we can take away 2 moles. It entirely depends on us. So, what is the total amount and what we are abstracting or adding, they have got no dependence. So, n and dn are independent. So, as n and dn are independent of each other, we have this m, this two terms will be 0, this dm minus del m del t at pxi dt minus del m del p txi dp mi bar dxi equal to 0, and m minus summation of mi bar into xi, that is equal to 0, I equal to 1 to n, these also I equal to 1 to n. So, this relation is very important one. What we are getting from here? M, the specific solution property, is the mole fraction weighted average of partial molar property. That is called summability relation. Right, that is the typical summability relation. The other one, you see, there is a dm. So, from here we get that dm is equal to mi bar dxi plus xi dmi bar. So, that we substitute here. And as a consequence, what we will get? If I substitute it here, see this mi bar dxi and minus of mi bar dxi, they will cancel out. These two terms will cancel out. And we will have a relation xi dmi bar I equal to 1 to n minus dmi bar minus del m del t at constant pxi dt minus del m del p at constant txi dp equal to 0. So, this is the very well known Gibbs duhem equation. Right, the previous one is summability and the second one is Gibbs duhem. So, at constant temperature and pressure, Gibbs duhem equation becomes xi dmi bar equal to 0. Right, this is the form at constant temperature and pressure. So, you have got two understanding, one is summability, another is this Gibbs duhem and Gibbs duhem specifically at constant temperature and pressure. But this equation is not leading us the direct explicit functional relation between mi bar to m, right, different other these functions of m. Okay. So, we want to get this reverted. Here m is expressed as a function of mi bar, here there is a relation, but that what we are thinking of, that mi bar is expressed as a function of m or its derivative with respect to xi and all. That is only possible for a binary system, okay? Because we have only, when think about the degrees of freedom in binary solution, we have M1 bar and M2 bar. These two are the partial molar properties, and we have two equations. One is summability, another is Gibbs duhem at constant temperature pressure. We consider constant temperature pressure equation for simplicity, right? So, for a binary system, we can express M1 bar and M2 bar as an explicit functional relation with X, okay, or X1, or sorry, M and X1. So, our next point of discussion will be the binary solution. For a binary solution, the number of compounds equal to 2, components equal to 2. So, summability gives you what? M is equal to M1 bar X1 plus M2 bar X2. And Gibbs duhem gives you at constant, we consider it at constant temperature and pressure. dm is equal to, sorry, x1 dm1 bar plus x2 dm2 bar equal to 0. Now, before going into that exact mathematical solution, we must note that mi bar, its partial molar property, right? Let us define some more properties. Mi is the pure species property and M is the molar property of the solution. That is property per unit mole, right. Now, you see in a solution, if xi tending to 1, mi bar must tends to mi, because the solution becomes tending towards a pure species I, right. So, limit, or we can write mi is limit xi tending to 1 mi bar, and also the molar solution property will also tends to pure species property, that same as limit xi tending to 1 m itself, right. Now, the other extreme, if I set that mi or xi tending to 0, what will happen? Here the partial molar property will not vanish, but even it happen, it may increase than the pure species property, and that is called infinite dilution property, right. Infinite dilution property, mi bar infinity. What is that? Mi bar infinity is limit xi tending to 0 mi bar, right, but not m. So, it may happen, right, this mi bar infinity is not at all 0 and mi bar infinity may be higher than the pure species property, okay. So, with that understanding, let us proceed for binary solution. So, you see that if you take the differential of this, so dm is equal to m1 bar dx1 plus m2 bar dx2 plus x1 dm1 bar plus x2 dm2 bar. So, this entire bracket term will be 0 as per Gibbs duhem equation. right. So, dm becomes m1 bar dx1 minus m2 bar dx1, as dx1 is equal to minus of dx2, because x1 plus x2 is constant. So, dm dx1 is m1 bar minus m2 bar. Let us say this is equation 3, whereas this is equation 1, sorry, this is equation 2 and this is equation 1, right. Now, 1 plus 3 into x2, right. So, m plus x2 into dm dx1, that is the left hand side, and on the right hand side m1 bar x1, here m2 bar x2. So, if we add, that will be m1 bar, and here m2 bar x2, and here minus of m2 bar x2, so that will cancel out. So, from here we can write that m1 bar is equal to m plus 1 minus x1 dm dx1. We have to write it explicitly as a function or in terms of x1. So, this is equation 4, and alternatively, if I have to eliminate this m1 bar, right, if I have to eliminate this m1 bar, so 1 minus 3 into x1. So, m minus x1 dm dx1. Now, you see m1 bar x1 and here m1 bar x1, right, and it is a minus sign. So, that will cancel out, and here m2 bar x1 minus will change its sign. So, it will be plus, because we are subtracting. So, it will be plus m2 bar x1 and here m2 bar x2. So, upon addition it will be m2 bar. So, we can write m2 bar is equal to m minus x1 dm dx1, right. This is equation 5. Now, you see how to solve this type of problem. This is a very common problem repeatedly given in GATE. Just like typical example, we see the molar specific, the specific solution enthalpy is 400 x1 plus 600 x2 plus x1 x2 40 x1 plus 60 x2, right. It is given. Now, if I have to apply this equation, if I have to apply these two equations in order to get h1 bar and h2 bar, first we have to convert this x2 to x1, because this is a total derivative, not a partial one. So, h 400 x1 plus 600 1 minus x1 plus x1 1 minus x1 40 x1 plus 60 1 minus x1. And if you do that, you will get this equal to 600 minus 180 x1 minus 20 x1 cube. So, that is the h expression explicitly represented in terms of x1. So, dh dx1 is minus of 180 minus 60 x1 square, right. So, h1 bar expression, which is h plus 1 minus x1 dh dx1, if I substitute that, it will be giving you 600 minus 180 x1 minus 20 x1 cube minus 180 x2 minus 60 x1 square x2, right. We can do it, and if we replace this, because we have replaced this h is there in terms of x1 and x2, if we replace this, I will get directly h1 equal to 420 minus 60 x1 square plus 40 x1 cube, right. And similarly, h2 bar, which is h minus x1 into dh dx1, upon substitution I will get this as 600 plus plus 40x1 square. So, these are the expressions of the partial molar properties. Now, we may be interested in finding the pure species and infinite dilution property. See, H1 is equal to limit x1 tending to 1, H1 bar, and that is also limit x1 tending to 1, H. So, H1 bar, if we go by H and we are substituting x1 equal to 1, right. So, x2 equal to 0. So, these two terms will vanish and that will be 400. So, this is 400 joule per mole, and also if we go by H1 bar if I substitute x1 equal to 1, so 420 minus 60 plus 40, right. So, it is again 400. So, it is all the same. And H2 bar or H2, its limit x2 tending to 1, H2 bar, and limit x2 tending to 1, H. So, if x2 tends to 1, x1 tends to 0, so it is 600 directly from here. So, 600 joule per mole. And let us check it for this equation. This is 600, x2 tending to 1 means x1 tending to 0. So, it is again 600, it is same. Now, let us solve for H1 bar infinity. For that, we require H1 bar expression in terms of x1, x2, right. We cannot solve it from H as unlike previous case of pure property. So, H1 bar, when x1 tending to 0, 420, H1 bar, x1 tending to 0. So, this vanishes. So, answer is 420 joule per mole, and what we observed that it is greater than the pure species property. Similarly, H2 bar infinity, x2 tending to 0 means x1 tending to 1, so it is 640, and again that is greater than the pure species enthalpy of 2, right. So, what I was saying that infinite dilution property, that does not mean that whenever the solution is infinitely dilute, the property will also vanish. It may increase than the pure species. Okay. That depends on the type of the system and the type of the property we are discussing about. So, there is some graphical interpretation also. Say here, in order to solve for this M1 bar and M2 bar, we need this equation M, just like here. H is expressed as a function of x1, x2. What are the steps? That x2 we have converted to x1 as 1 minus x1. We have simplified the expression, then evaluated the derivative and substituted in these two expressions. We have got M1 bar and M2 bar, and from there we have also calculated this pure species value and infinite dilution value. However, if M is given in terms of some discrete data point for different values of x, then we do not have to go by statistical regression to generate this equation. Instead, we can solve all the properties graphically, but we will not get any expression. We will not get any expression of M1 bar and M2 bar like the previous case, but we can solve for M1 bar and M2 bar for a given x1 numerically, or rather graphically. Graphical interpretation of M1 bar, M2 bar, M1 bar infinity, M2 bar infinity, M1 and M2. What are they? See, what will be given to us? Some scattered data points like this, 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 this and this. So, we will join them by a smooth line and we will get some sort of curve like this. So, manual, right. So, you have got this M versus x1 plot. This is x1 equal to 0, x2 equal to 1, this is x1 equal to 1, x2 equal to 0. Right. Now, dm dx1 means what? It's the slope of the tangent drawn at any point. Like here, let's say the point. We have the point here, and we have drawn a tangent. And the tangent has got an intercept I1, and here the intercept is I2. Right. So, you have drawn the tangent at this point. So, this is x1, definitely this must be m. So, you see that if I name the point as P, this is A, this is B, and if we think of a triangle like C, and here it is D, right. So, dm dx1, okay, for what I can say, this is the tangent drawn. Let me use a solid line, okay, not this one. We can write the slope expression from this triangle or from this triangle. So, PAB and PQ, let us say R. Okay. So, for triangle PAB, so we have dm dx1, which is tan of this angle PAB, and it's perpendicular by base. So, BP divided by AB, right. Now, BP is how much? This BP is how much? So, we can write BP as M minus I2, because this much is M, see, this much is M and this much is I2. So, M minus I2 is this much, and this is x1, right, AB is x1. So, we write x1. So, I2 is M minus x1 into dm dx1, and from our analytical calculation this is M2 bar. So, I2 is M2 bar. Now, for triangle PQR, dm dx1 again we can write that this much, this is QR, or rather we can say it is tan of angle QPR, so which is QR divided by PR. So, QR this much is I1 minus M. I1 minus M is this much. So, I1 minus M, and PR is, this is 1 and this is x1. So, this is 1 minus x1. So, it is 1 minus x1. So, I1 we are getting as M plus 1 minus x1 into dm dx1. So, by definition this is M1 bar. So, from the intercept measure, actually we can calculate the partial molar property at some specific point. Okay. Now, so this is the graphical measurement of partial molar property, and how we can measure this infinite dilution property? Let us say this is the graph. So, if I shift that point P here, right. So, we are drawing the tangent to the graph here, x1 is equal to 0. So, this I2 must be what? This I2 is limit x1 tending to 0, M2 bar, and that is what? M2. So, this much is pure species property M2. and the I1 here, I1 is limit x1 tending to 0, because the point is here, point is not this, we are drawing the tangent here. So, I1 x1 tending to 0, m1 bar, so this is m1 bar infinity. So, this much is m1 bar infinity and this is m2, right. So, similarly, if we draw the tangent here, this is m1 and this will be surely the m2 bar infinity. Okay. So, if I draw the tangent and see the curve also intersect the tangent intercept at the same point. So, that justifies that y limit m or limit xi tending to 1 m is also equal to mi. Okay. So, from there we can graphically calculate, there is the interpretation, graphical interpretation, and from there even if this equation is not given, we can graphically calculate the partial molar properties at a specific concentration. We can also solve for pure species property and infinite dilution property. So, with that understanding of this partial molar property for the binary system, let us move on to the calculation of partial molar property in a multi-component model mixture, right, and that model is definitely the ideal gas mixture. So, we are going to discuss this partial molar properties in ideal gas mixture. Now, you see this ideal gas itself is a model of real substance where we do not have any intermolecular interaction. So, if no interactions are there, the pure species property must be equal to partial molar property, right, and that gives rise to Gibbs theorem. What it states? It states that partial molar property of a component species in an ideal gas mixture at a temperature and pressure is equal to the pure species property of the same component at the same temperature but at partial pressure. Note that when we are mixing some components in the gas phase to generate a gas mixture, the pressure of the individual component is not the total pressure, it is rather the partial pressure. And what is the definition of the partial pressure? Precisely the theoretical definition. If let's consider a gas mixture. If any one of the component occupies the same volume at the same temperature, the pressure exerted by the component is the corresponding partial pressure of that component in the mixture. Correct? So, the volume or the sameness of the volume, the equality of the volume is being used in the definition of partial pressure. So, that is why Gibbs theorem actually it's valid for all properties except volume, because in the partial pressure definition we are using this idea of volume, right, valid. So, this is valid for all properties except volume, and xi is the respective mole fraction. Xi is the respective mole fraction. Now, you see that using this Gibbs theorem, next we will try to relate these different properties at the same temperature and pressure. We will try to we will remove this partial pressure, and basically we will try to formulate that what is mi bar ig as a function of mi ig. So, that is our target, right. So, we will choose different properties. First, enthalpy. We have Hi bar Ig Tp, according to Gibbs theorem, Hi Ig Txip, and that we can write as Hi Ig Tp. How we can write that? As enthalpy of ideal gas is independent of pressure, right? So, our final form will be Hi bar Ig at any temperature and pressure, it is equal to Hi Ig, right? The second, we will discuss about entropy. We know, you see, that for any pure species dSi Ig equal to Cpi Ig dln T minus R dln P. It is a pure species, it is not for a mixture, right. Now, we will integrate this equation from a state Xip T to a state Pt, but it is not a mixture, it is a pure species, right. But partial pressure, but think like that we are integrating a pure species ideal gas entropy equation from a pressure it would exert if it is in a mixture with a mole fraction Xi. So, definitely though I am writing it as Xip, but Xip has got some numerical value. So, from one numerical value to another numerical value we can obviously integrate. So, we will write this is SiIg T P minus SiIg, it is pure form T Xip, and on the right hand side as there is no temperature change this will be 0. So, minus R ln P divided by Pxi, so R ln Xi, right. Now, you see according to Gibbs theorem SiIg pure species entropy at T Xip must be equal to Si bar Ig at Tp. So, SiIg T comma P minus Si bar Ig T comma P equal to R ln Xi. So, Si bar Ig T comma P or SiIg T comma P minus R ln Xi. So, that is the relation of partial molar entropy and pure species entropy for ideal gas mixture. So, third is Gibbs energy. So, Gibbs energy Gi bar Ig equal to Hi bar Ig minus T Si bar Ig. So, Gi bar Ig equal to C, Hi bar Ig equal to Hi Ig and T Si bar Ig is equal to Si Ig minus R ln Xi. So, Hi Ig minus T Si Ig plus RT ln Xi. So, this is by definition is a pure species Gibbs energy plus RT ln Xi, which is Gi bar Ig. So, these three are the relation. Now, we will try to understand that property change upon pure mixing. Pure mixing means we have discussed it for entropy in entropy calculation, that is no change of temperature and pressure, right. So, this delta M mix is basically equal to M minus solution property MIXI summation. In pure form, what is the weighted average and actually what is the solution property, specific solution property. This per unit mole. and we know that from summability that this is mi bar xi minus mi xi. So, obviously, delta m mix is mi bar minus mi into xi I equal to 1 to n. Right. Now, using this definition, we can say that there is no enthalpy change for ideal gas mixing. So, ideal gas mixing is athermal, there is no thermal effect. Okay. Delta S mix Ig Si bar minus Si equal to minus R ln xi. So, minus R summation of xi ln xi, always positive, right, because xi is negative. So, log of xi will be negative. Sorry, xi is a fraction, so log of xi is negative. And del G mix Ig is simply Gi bar minus Gi is RT ln xi. So, it is RT summation of xi ln xi, and it is always negative. The Gibbs energy must decrease for a spontaneous process, and mixing here for ideal gas, definitely the gas phase must be spontaneous. So, we have this Gibbs energy, right. So, this is Gibbs theorem and respective change of Gibbs energy that we have actually calculated. So, next you see, again we will go back to the pure state. Again we will go back to the pure state for ideal gas. Again we will go back from here to this pure state and try to first map that how the equation is going to change for non-ideal gases, right. For pure ideal gas, first we will try to write the Gibbs energy. Now, we are actually going towards the measurement of Gibbs energy. Okay. So, how we can measure the Gibbs energy of a non-ideal gas, that is our primary problem, and we will try to solve the problem. Let us see how we can solve this problem. So, you see that for pure species ideal gas, we have what? dGi equal to minus SiIg dt plus ViIg dP. Now, we further simplify it at constant temperature. dGiIg is equal to ViIg dP, which is nothing but RT by P, and dP by P is equal to dln. Right. So, we get dGiIg is equal to RT d ln P, and this is an equation for ideal gas at constant temperature. So, directly from here, equation for real gas. We will try to go for real gas. See, and that idea was introduced by Lewis, this American physical chemist. He introduced that, okay, here we have got a functional relation in differential form, right, like dy is expressed as a function of dx. Okay, dy is expressed, dy is, let us say, it is Gibbs energy, and dx, that is this dP. So, it is expressed as a function of Gibbs energy, and there is a mathematical form. Okay. So, we will keep this mathematical form intact, right. Here this is a reverse directional introspection into that equation. Generally, we always try from scratch and we keep this independent variable same, we try to change the dependent variable, right. Like dependent variable, like you see that if I think that volume which can be measured from pressure and temperature for ideal gas, it is RT by P, for non-ideal gas it will be ZRT by P. So, independent variables are kept same, but the dependent variable changes. One is the volume of ideal gas, another is the volume of real gas. So, and the mathematical structure also changes. Here, what was the strategy? That we will keep the mathematical form of this differential relation between independent and dependent variable same, right. The dependent variable will also be kept same, but independent variable we will change. But we do not know what is the independent variable, that is the beauty of this concept. We introduce a new independent variable, and that is pure species fugacity. So, now you see that I can introduce any definition, but unless I give a protocol for its measurement, there is no point in introducing this definition, and that is called the closure of that definition. So, what will be the closure of Fi? So, you should give a protocol by which we can measure, a technique or method by which we can measure this Fi, right. So, for that, so what will be the closure? To answer this question, we introduce residual property. MR as real gas property minus the corresponding ideal gas property, and this is valid for a mixture of real gas and ideal gas, and as well as a pure species real gas. So, valid for mixture as well as pure species. So, we can say that GR is equal to a GIR for a specific species, it is GI minus GIIG. So, DGIR is equal to DGI minus DGIIG, and that is equal to RT d ln Fi minus RT d ln P. So, it gives rise to DGIR RT d ln Fi by P, a dimensionless quantity. Note that fugacity, as we are keeping the same structure, the fugacity must have the same dimension as that of pressure, but it is not equal to pressure, right. So, fugacity by pressure must be a dimensionless quantity, and we call it pure species fugacity coefficient, RT d ln phi I, right, where phi I pure species fugacity coefficient, right. So, now if I integrate it, GIR, and this is an equation at constant temperature, because this constant temperature, this frame is intact. So, if I integrate GIR equal to RT ln phi I, plus the constant will be dependent on temperature, right. So, what is observed that at or for ideal, this equation must be valid for ideal gas as well. So, for ideal gas you see phi I is 1, GIR is 0. So, BIT, which is independent of the fact that whether it is real or ideal, but depends on the species and temperature, must be equal to 0 for all species. So, from here we have GIR is equal to RT ln phi r. Now, GIR we will calculate in a different way from here using the fundamental definition of Gibbs energy. So, this is dGIR and this here at constant temperature. Now, at constant temperature we have GI is equal to VI dP, dGI, and here dGI Ig equal to VI Ig dP. So, dGIR is equal to Vi minus Vi Ig whole bracket dP. So, this is residual volume of that species GIR, right. Now, you see Vi we can write for real gas Zi RT by P, Vi Ig equal to RT by P. So, dGIR is equal to Zi minus 1 RT dP by P, right. Now, dGIR already we have solved, it is RT dln phi I, which is Zi minus 1 RT dP by P. So, RT cancels out. Now, if I integrate from 0 pressure, so from 0 pressure to this pressure at which we want to calculate the fugacity coefficient, at 0 pressure the fugacity coefficient will be 0, because at 0 pressure a real gas behavior tends to that of ideal gas. So, for the lower limit it will be not 0, this phi I will be equal to 1. So, this is phi I by 1 actually, and on this side 0 to P Zi minus 1 dP by P, and this gives you the closure of fugacity definition, because Zi is a well documented quantity or a parameter. We know how it depends on pressure and temperature. Now, if I want to calculate the fugacity at a specific temperature and pressure, so I will see that how at that specific temperature how Zi varies with pressure. So, I will substitute those values, and if analytically it is not possible, we will numerically integrate it, get the value of phi I, and from phi I we can calculate this Fi upon multiplying it by pressure. So, residual Gibbs energy we are now able to directly calculate for a pure real gas, right. So, with that idea, we'll stop here, and in the next session we will discuss further that how we can use the virial equation or equation of state, cubic equation of state, to calculate this pure species fugacity and fugacity coefficient, and next we will move on to that fugacity and fugacity coefficient concept, how it has been extended for a real gas mixture. Thank you.